So here's a few pictures just to kind of demonstrate the security boundaries of what this looks like. It's RBG1, so as you can see, the security boundary of the randomness source is separate from the security boundary of your actual RBG1 construct. And so this kind of reinforces that you know that's going to be outside of your computation environment, and again, no reseeding destroys after done. RBG2 constructions, in this case, the DRBG is contained within the same security boundary and cryptographic module. Here you can reseed upon application request or based on your reseed policy. You must reseed after 2 to the 17 bits of output. So again, there may be some reworking needed in the implementations of your DRBGs to handle this. And next we'll move on to RBG3s. So this is the XOR implementation. You can see also the entropy source got to be inside of the RBG security boundary. Here the optional condition function is input into the XOR function, and then of course you're feeding the DRBG. As Josh mentioned, you may be using externally provided input or internally provided input outside of just your entropy source. And then of course the DRBG is also feeding the XOR operations, getting full entropy out. Okay, this is the RS version. So in the RS version, same security boundary. In this case, the output is coming directly out of the DRBG, full entropy output. And there's some interesting diagrams around what this looks like. So when you're requesting a generate out of the RBG itself, you get a reseed every time, so prediction resistance. And then the other interesting thing is that the DRBG can be made available to your application directly. And so you do get into this case where maybe you're making calls into the RBG construction, you see the reseeding happen, but then your application accesses that DRBG directly. It's able to do so without reseeds occurring, and then the subsequent request that comes into the RBG construction will force a reseed.